Hey guys, Dr. C here, and welcome back to Data Analysis and Statistics for the Social Sciences. In this video, we're going to continue our discussion about comparing two populations. Last time we talked about how it is you can compare the mean for one population against the mean of another population. In this video, we're going to do the same thing, but we're going to talk about things in terms of proportions. So you're able to look at one group and the proportion of people that have some belief, some opinion, some characteristic, and then you're going to be able to compare that to some other group and see how the proportion for that first group differs compared to that proportion for that second group. And again, this is an important thing to be able to do. You know, sometimes in life we can look at two different groups. We can ask them a simple question like, who are you going to vote for? And we can look at the results, and sometimes we'll see that it's really clear that one group is going to vote for one person more than another group. So if you look at this slide, it's pretty easy to see that there are more yellow dots in sample B than in sample A. But other times we'll be in a situation that's more like this. So you go out in the world, you talk to two different groups, you ask them, who are you going to vote for? And when you look at the results, visually it's really hard to tell whether or not they're the same or different. So that's where we really need the statistics. We need some kind of tool to help us do that fine-tuned analysis to really look at these two groups and say, okay, are they different or not? So the tool that we use to compare two groups is this difference between two population proportions method. So here we test bold claims that two population proportions are the same. Now, in order to use this tool, there are several assumptions that need to be checked out. So if any of these assumptions are grossly violated, then we can't use this tool. Or if we did use this tool, then our conclusions would be wrong. So our first assumption is that there are two populations. So there need to be two groups that you want to compare. Again, these could be things like men versus women. These could be people who have been the victim of crime in the past versus those who have not been the victim of crime in the past. It also assumes that we're talking about proportions. So there's got to be some categorical variable out there that you want to explain. So it could be the proportion of people who have been the victim of crime in the past, or it could be the proportion of people who've consumed an alcoholic beverage with their parents or not. So eventually what we like to do is look at those categorical differences and say, okay, are those differences different between groups? You know, are parents more likely to drink with their sons than their daughters? Things like this. We also have our old friend, the independence assumption. So again, this is the idea that when people respond to our surveys, that they're letting us know their thoughts, their opinions, their beliefs, and they're not being influenced by anyone else who took one of our surveys. So for your guys' research, I had people go out on campus and collect information from students, and we did this one at a time. So everyone who wrote in on the survey let us know what they were thinking, what they believed, and they weren't being influenced by anyone else's opinions. We also have this random assignment assumption. And again, in this course, the random assignment assumption is going to be violated. So whenever we're thinking about the groups we're comparing, ideally we want people to be assigned to those groups at random, say by flipping a coin. But a lot of the questions that you guys are going to be investigating, it might not be feasible to do that. So we might not be able to flip a coin at birth and randomly assign the students we talk to into one gender group or the other. Or we might not be able to flip a coin and take somebody and make them a senior, and then make somebody else a freshman. The final assumption is this large sample assumption. So in order to use this tool, you need to have a lot of data. So we'll talk about what that means in a minute. So in order to use this tool, we conduct a test of hypotheses. So again, we've got our 6 steps, the same 6 steps we've been talking about all semester. So step 1, we're going to state our null and our alternative hypotheses. Step 2, we're going to set the significance level. Step 3, we're going to determine the appropriate statistical method and then check the assumptions. Step 4, we determine the p-value. We're then going to use a flowchart. You want to show your work. Step 5, we're going to compare the p-value to the significance level. You're going to reject or fail to reject that null hypothesis. And then step 6, we interpret our results. So to show you guys how this comparing two population proportions method works, I'm going to draw on some speeding data that I've been collecting. So some of my research is interested in crime prevention. So I want to know what is it we can do to help people drive a little safer around campus. So I've got two different groups that I'm interested in. So those who are driving in the morning during rush hour and those who are driving in the afternoon. And I'm curious about whether or not the time of day matters in terms of how fast people are driving. So here I've got this categorical variable about whether people are speeding or not. So what I do is I take my data and I create what's known as a cross tabulation. So here you'll notice there are two large rows in this table and two large columns in this table. One for afternoon, another row for morning, and then for each of these rows I can see the percentage of people who were speeding. So in the afternoon, 3.5% of people were speeding, while in the morning, 69.3% of people were speeding. My thinking here is that, people during rush hour tend to drive faster than those in the afternoon. But, there might be some doubting scientist out there who says, actually, there's no difference between the two times of day. People drive however they want to drive, whenever they want to drive. So I want to take this doubting scientist claim and test it using data. So step one, we state our null and our alternative hypotheses. So again, this is our planning stage. So we want to be really clear about what that doubting scientist hypothesis is, and then we want to be really clear about the hypothesis that we think is going on. So in this situation, the null hypothesis is going to be that there's no difference in speeding cars between morning and the afternoon. And the alternative hypothesis in this case, the hypothesis that I think is happening, is that the morning cars are more likely to speed than the afternoon cars. Again, when it comes to this null hypothesis, it's always going to have one format to it, that doubting scientist hypothesis. It's always going to say that the proportion for one group is the same as the proportion for the other group. Now, when it comes to the alternative hypothesis, again, we have some choices. So it could either be a not equal to test, a less than test, or a greater than test. So we might think that the proportion for one group is less than the proportion for the second group. So if that's the case, then we're doing a less than test. Or we might think that the proportion is greater for one group compared to the other group, in which case we're doing a greater than test. Sometimes in life, we might think that two groups are different. We might not know how they differ. So if that's the case, then we could do a not equal to test. In this course, we're primarily going to focus on the greater than test or the less than test, because usually when we pick our groups to compare, we have some belief ahead of time about how those groups are going to differ from each other. So for some reason, SPSS is a dinosaur and still doesn't really have a good comparing two population proportions method. So what we need to do is we need to use another piece of software to make up for the deficiency of the software we're using. So we're going to go to this website called Social Science Statistics as a calculator that you can use online to find some information that we need to get that p-value. Now there's a warning that I need to give you when working with social science statistics. So when it comes to this website, you're going to take your data, some of it that has been provided to you by SPSS, and you're going to plug it into the website. So the problem here is that the order in which you plug in the information, it matters. This is kind of hard to think about because as a smart thinking human being, you know that you can say some things in different ways and still mean the same thing. Unfortunately, when it comes to software, it doesn't work like that. So you as a thinking person would recognize that if I said that the proportion of people who are speeding in the morning is the same as the proportion of people who are speeding in the afternoon, that's the same exact statement as saying the proportion of people who are speeding in the afternoon is equal to the proportion of people who are speeding in the morning. So as a human being, we can realize that those two statements are equivalent, but unfortunately, the software doesn't know how to do that. So what you need to do is just be really consistent. You're going to look at your null and your alternative hypotheses. You want to make sure that the order of the groups stays the same for both of those. And then you need to make sure that that order is also preserved when you put the information into the social science statistics website. So if you don't do this, then your conclusions will be wrong. So when you go to the social science statistics website, you're going to see fields that look like this. So here we have sample 1 statistics, and here we have sample 2 statistics. So what is sample 1? What is sample 2? What is group 1? What is group 2? The way I determine this is I look at my hypotheses. So again, I make sure my null and my alternative hypotheses, that the order in which I list the groups and talk about them is consistent. And then from there, I use that to determine what my groups are. So if I look at my null hypothesis, here it says that there's no difference in speeding cars between morning and afternoon. So because I said morning first, that makes it the first group. Afternoon comes second, so then it becomes the second group. So I need to make sure that when I put in the statistics, so here it's 427 people and 0.693 of them were speeding, that this is what I'm putting in for the morning group. And if we look back at this table, we can see that that's consistent. So for that morning group, we had 427 people, and we have 69.3% of people who were speeding at that time. So then we do the same thing for the second group. So I go back to that table, I get that percentage, and I convert it to a proportion. So here it becomes 0.035, and then I look at the number of people in that second group, the cars that were driving in the afternoon, and I write in that number there, so 173. Step 2, we set our significance level. So again, we've got this doubting scientist hypothesis, this idea that there's no difference between the two groups. And we want to test that using data. So we're basically looking at that claim that person has made, that doubting scientist has made, and we're going to make a decision about whether we think it's true or not. So because we're making a decision, there's always a chance that we're the ones who are going to be wrong. So what we do is we become really conservative, and we say to ourselves, okay, we're not going to reject what that doubting scientist is saying unless there's a very small amount of risk that we're the ones who are making the mistake. So if there's a lot of risk that we're going to make a mistake in our conclusion, we don't want to do it. But if there's a very little risk, then it's fine. Step 3, we then determine the appropriate statistical method and then check all of the assumptions. So here we're using this difference between two population proportions method. It assumes two populations. This is okay because I'm talking about cars in the morning versus cars in the afternoon. It also assumes population proportions. So this is also okay. So the variable that I'm really trying to explain is whether people were speeding or not. So it's a categorical variable. So every car I looked at, I checked a box of whether or not they were going above the speed limit or not. Assumption 3, again, is our independence assumption. And I'm going to say that this is okay because the cars don't know or don't influence each other. And then for step 4, we have our random assignment assumption. So in this case, it's not okay. It's been violated. You know, when you think about the cars that I observed, I didn't randomly assign them to the different driving times. So people got to pick their own driving times. So in this case, it's been violated. In your guys' research, it'll probably be violated too. But what you want to do is just put a note that says that it's okay for learning purposes. Now, when it comes to using this difference between two population proportions method, we have this additional assumption, this large samples assumption. So in order to use this tool, we need to make sure that we have lots of data. And the way we know we have lots of data is by checking these 4 criteria. So when it comes to how this works, you need to think about the sample size for the first group. You're also going to need to know the sample size for the second group. You need to know the proportion of individuals with the feature that you care about for the first group. And you also need to know the proportion of people with the feature you care about for that second group. So if you want to figure this out, you're going to have to go to that cross tabulation to get those numbers. So once we get those numbers from this cross tabulation here, what we're going to do is we take them and we plug them into those criteria. So for that morning group, I take 427, which is the number of cars that I saw in the morning, and I multiply it by 0.693. I then get the number 295.91. So this number is bigger than 5, so this criteria checks out. I then take 427 and I multiply it by 1 minus 0.693. Notice here that I get a positive number, and this number equals 131.09. This number is also greater than 5, so this criteria checks out. For the afternoon group, I then do the same thing. So I take 173, which is how many cars I saw driving in the afternoon. I multiply it by the proportion of people that I saw speeding, which was 0.035, and I get the number 6.06. So this number is also bigger than 5, so it checks out. I then take 173, multiply it by 1 minus 0.035, and then I get this number here, 166.95. So all 4 of these criteria check out. So in this situation, when it comes to my speeding research, my sample is large enough. Now when it comes to your guys' research, you guys are going to have to check these criteria yourselves. So what I recommend is you use this slide as an example. So pull out a calculator, try to do these calculations here, and try to get the same answers that I got. So once you're able to get the same answers that I got, then you can go to your research and you can get your numbers and use that same strategy that you found to get the right answer. So for step 4, we're gonna go to social science statistics. You're gonna, again, put in your information for your first group, put in your information for your second group. You'll check the radio button next to 0.05. You'll check the radio button next to the words two-tailed, and then you'll click OK. You'll then get this information down at the bottom. So this information might be blue, it might be red. So this website is trying its hardest to help you understand whether your results are significant or not. But again, you can't trust the software, guys. So unfortunately, social science statistics has no idea of what your alternative hypothesis is. Because it doesn't know what your alternative hypothesis is, then the information it gives you and the conclusions it's trying to tell you about, they could be wrong. So what we need to do is get the crucial information from this website, and then we go to the flow chart to really find that true p-value. So here I write down the z number, which in this case is 14.6025, and then I write down this p number, which in this case is 0.00001. I then go to the flow chart. So when it comes to this flow chart, I need the z number, I need that p number, I also need my alternative hypothesis. So the alternative hypothesis is crucial because that's going to tell us which of these 3 different paths to go down. So if we're doing a less than test, we go down that first path. If we're doing a not equal to test, we go down that middle path. If we're doing a greater than test, we go down that third path. So here I look at my alternative hypothesis. Here I can see that it's a greater than test. So that tells me I need to go down that third path. So I'll zoom in. And then what I need to do is I need to look at that z number. So if that number is positive, I'm going to do one thing. If it's negative, I'm going to do something else. So here I look at the number and it's 14.6025. This is a positive number. So since it's a positive number, I'm going to continue down the path to that final box. So once I'm in this final box, then I can see what it is I need to do to find the true p-value. And the box tells me that I need to divide the value in the phrase, the value of p is, by 2. So in this case, I take that p number, that 0.0001, and I divide it by 2, and I get this new number, which is 0.000005. And that's the true p-value. So with step 5, I'm then going to compare the p-value to the significance level. If the p-value is really small, then we reject the null hypothesis and accept the alternative hypothesis. If the p-value is really big, we're going to fail to reject the null hypothesis, and then we're going to conclude that it's possible that the null hypothesis is true. So in this situation, I've got a p-value, so the number 0.000005 is a smaller number than 0.05. So since the p-value is less than the significance level, I'm going to reject the null hypothesis and I'm going to accept the alternative hypothesis. And then with step 6, we interpret our results. So again, we need to be able to tell other people what it means to say that we've rejected the null and accepted the alt. So we need to provide two interpretations. We need a technical interpretation, in case we're presenting our findings to anyone who's taken a stats course. And then we also have our everyday interpretation. So this is the interpretation that we share with the world to let them know about the discoveries we're making about life on campus. So with our technical interpretation, we say that at the alpha equals 0.05 level, we have sufficient evidence to conclude that morning cars are more likely than afternoon cars to speed over the long run. And then with our everyday interpretation, we have this idea that the doubting scientist is wrong. So the cars speed more in the morning. So when it comes to your guys' interpretations, I want them to be as close to mine as possible. So anything in these gray boxes you want to swap out for your research context, your findings. Notice here that I've got the word sufficient. If you find that there's a difference between the groups, if you reject the null, then you'll say sufficient too. But if you fail to reject that null hypothesis, then you got to change that word. So then it becomes insufficient evidence to say that there's a difference. And again, you really want to think about this everyday interpretation. You guys are making discoveries about life on campus, and you want to share them with people in a way that normal people can understand what you're saying. So, are the groups different? Yes or no? How are they different? Okay guys, so that's the video. So in this video we talked about this powerful tool for looking at two different groups and determining whether or not they're different or not for some proportion that we care about. And again, this tool is super important. There's always change that happens in the world. People at organizations have some new way of doing things, and they're always curious about how the new way of doing things compares to the old way of doing things. So with this tool, you can then conduct that study. You can go out and collect your own data, and you can see, okay, do these two groups differ or not? Does the new way of doing things, is it actually better than the old way of doing things? So powerful stuff, guys. If you have any questions when trying to use this tool, just let me know.